Okay, this is the second video. Your first video was a review on limits. And so now we're going to do the last limit strategy, which we couldn't learn in August or September because you need to have a solid comprehension of derivatives in order to do it. So our very last limit strategy, this is from the first video, our very last limit strategy is called L'Hopital's rule. So I'm just going to put LR right here, and we'll go back to our L'Hopital rule packet that we accessed for video 1. And we're now going to tackle a family of limits that seem to lead us to DNE. Okay, so I'm actually starting with one that we already know the answer to, but reminder that we only know this answer because we straight up memorized it. So if we were just looking at this problem fresh in August or September, we would go through all of our strategies and say, total bummer, can't use substitution because you can't put a 0 into the denominator. No one ever taught me any algebra. I absolutely do not know how to graph this without a graphing calculator, and we would have been stuck. So I would like you to follow along, and we are going to learn something completely new right now. If you pop a 0 in, the numerator is sine 0, which is 0. If you pop a 0 into the bottom, you also get 0. So when you plug a 0 in, you get 0 over 0. If you type 0 over 0 into your calculator, it will absolutely tell you error. You can't divide nothing by nothing. This is not a thing. This breaks math. This is an error. Okay, so if when using substitution method, you get 0 over 0. If when using substitution method, you get 0 over 0, we are going to be able to do a new trick. A French dude named L'Hopital. You should Google image him. He's a character. And then you actually need this little accent on the A, so I'm probably not saying it correct. French dude figured out this pretty neat thing. Okay, so the derivative of sine, just for fun, is cosine. The derivative of x is 1. You usually don't take derivatives of fractions this way. Reminder that we have the quotient rule. If you have a fraction, you absolutely don't just differentiate the top and differentiate the bottom. We had rules. We had quotient rules that we had to follow. But watch what happens with limits. If we don't consider sine x over x anymore, but instead we do a brand new problem, which is limit x approaches 0 of cosine x over 1, aka the derivative of the top and the derivative of the bottom. When we do this question, cosine of 0 is 1 and 1 over 1 is 1. Now we already know that that's the answer. I'm going to write whoa, even though probably you're not putting this together yet. So it turns out that every single time that substitution method would give you 0 over 0, the answer to this limit question is always, when you look with a graphing calculator, the answer to this limit question. So what L'Hopital figured out is that you can just take the derivative of the top and the derivative of the bottom, and then these are not equivalent. You can't differentiate this way. You can't just take the derivative of the top and the derivative of the bottom. We had a quotient rule to do a derivative. But it turns out that the answer to this limit question is going to also be the answer to our original limit question. You're going to need to hear that again, I think, before it sinks in. Okay. Next problem. This is one that we did during our review packet, and we found that the answer was 0 when we looked in a graphing calculator. You don't actually know how to do this question. You can't use substitution method. We don't know any algebra. You don't know how to graph this. So this is one where we would rely on L'Hopital's rule here moving forward to do this question. If I plug a 0 into the top, cosine of 0 is 1. 1 minus 1 is 0. If I plug a 0 into the bottom, I get 0. This is called the indeterminate form 0 over 0. You can't divide nothing by nothing. This is not a thing. This is a big fat error. But French mathematician L'Hopital figured out this trick that's true 100% of the time. So if you now that you're looking at a 0 over 0 indeterminate form, if you take the derivative of the numerator, which the derivative of cosine is negative sine, and the derivative of negative 1 is 0. And if you take the derivative of the denominator, and the derivative of x is 1, then you are not saying that the derivative of cosine x minus 1 over x is this, because in order to do the derivative of a quotient, you need quotient rule. But we are going to write a new limit question, not an equivalent limit question. These are not equivalent. But if you take the derivative of the top and you take the derivative of the bottom and you do this brand spanking new limit question, his answer actually just is always this answer as well. So check it out. If I do this question, sine of 0 is 0, 0 over 1 is 0. Compare that to the limit question from above. Okay, I'm seeing a pattern here. It's the same again. So what do I notice? Hopefully that they are the same. Okay, so to summarize, if you use substitution method and you get 0 over 0, instead of just saying, can't do that, L'Hopital figured out that if you take the derivative of the top and you take the derivative of the bottom, and then you do this brand new limit question, the answer to this brand new limit question was always the answer to our original limit question. And there's so much more to why this is, but I'm just trying to teach you the basics. If you're interested in this, you can look this topic up online and find out lots more. Okay, before I do a different indeterminate form, I want to scroll down real quick and just bust through a couple examples. So this question right here, I wouldn't know how to do without L'Hopital's rule, because I can't use substitution method because I'd get a 0 in the bottom. I don't know how to do any algebra. I don't know how to graph this. This is not an end behavior problem, and no one ever taught me anything about this as a memorized limit. So if I had put this on your limit test back in September, you would have been completely right to raise your hand in the air and say, you're crazy, we don't know how to do this one. Okay. So our very last limit strategy that I couldn't teach you in September because you didn't know enough yet is that if you use substitution method and you pop this in and you get 0 over 0, you can use a different limit to get your answer. So let's try it. If I plug a 0 in, e to the 0 is 1, 1 minus 1 is 0. If I plug a 0 in, 4 times 0 is 0. So I have the indeterminate form 0 over 0, which enables me to use L'Hopital's rule. So for L'Hopital's rule, I am writing a completely new problem. This is not how you take derivatives. You use quotient rule to take the derivative of a quotient. But the derivative of the top is 3e to the 3x, and the derivative of the bottom is 4. And now I can do this problem easily. If I plug a 0 in, e to the 0 is 1, 1 times 3 is 3, 3 over 4 is 3/4. And the answer to this limit question is the answer to this limit question as well. If you would like, you could go ahead and graph this in your graphing calculator or on Desmos and see that when the x's are trending towards 0, the y's are trending towards 3/4. I'm going to go ahead and scroll back up to our last indeterminate form. You don't need L'Hopital's rule for this. I taught you a lot with end behavior, but just in the spirit of like fully teaching you the topic, L'Hopital's rule works for problems like this as well. if you plug an infinity in and the numerator approaches infinity, and if you plug the infinity in and the denominator approaches infinity, then this is called the indeterminate form infinity over infinity. L'Hopital's rule works when you have infinity over infinity as well. You can take the derivative of the top, you can take the derivative of the bottom, and then you can do a brand new limit question where you are doing the derivative of the top and the derivative of the bottom. And the answer to this limit question is going to be our answer to the original. I would not recommend that you use L'Hopital's rule for a problem where you could use end behavior, because I feel like end behavior shows way more understanding. You have like a graphical understanding of the problem at large, but I just wanted to show you that L'Hopital's rule does work with this form as well. All right, let me scroll down and do another example or two. So for this problem here, I would actually not need L'Hopital's rule, because I could just go ahead and do some algebra and get the answer no problem. So I wouldn't use L'Hopital's rule, but let's see if it's a contender for, is it possible to use it? So as long as when you use substitution method, you get 0 over 0, which I get 0 over 0, then you are allowed to use L'Hopital's rule. So for L'Hopital's rule, you take the derivative of the top, you take the derivative of the bottom, and the answer to this question is the answer to your original question. Let's go ahead and plug this -1 in. We get -2. If we looked back up at how we would have done it in September with algebra, we also get -2. I'm going to go ahead and pause, and I'm going to do a few more of these problems, and then we can see if you got them right. Okay, I got 0 over 0, so I went ahead and tried L'Hopital's rule, derivative of the top, derivative of the bottom. The answer to this limit is also the answer to this limit, L'Hopital's rule. And then we're going to end on this one because 5 and 6 are a bit hard for the first day. So for this problem right here, the last thing I'd like you to kind of take in here is that when I used L'Hopital's rule, I got 0 over 0 again. So I took the derivative, If you get 0 over 0 again, then do L'Hopital's rule one more time. So I took the derivative, and the answer to this question is the answer to this question, which is the answer to this question. At this point, even without having done 5 and 6, those are the indeterminate form infinity over infinity, and it's a little harder. I think that you are now able to do all 10 of these problems on the third page. So your assignment's going to be to try them. I'm sure I will do them and post the answers in a day or two, but do an attempt on your own first. And I will see you soon. Okay, I hope this made sense.